Question 11. Prove by contradiction that for every real number x, where x lies between 0 and pi over 2 inclusive, sin x plus cos x is greater or equal to 1. So the question says, prove by contradiction. So we have to assume the opposite is happening. Assume that this statement, sin x plus cos x greater or equal to 1, is false. So they want us to prove that sin x plus cos x is greater or equal to 1. So the false statement, if this isn't true, is sin x plus cos x is less than 1. We could then square each side of this inequality, which means sin x plus cos x all squared is less than 1. And then if we expand the brackets, sin x plus cos x times sin x plus cos x means we'll get sin squared x, we'll get a sin x cos x and another sin x cos x, we'll have 2 sin x cos x, and we'll have a cos x times cos x cos squared x. If we square the 1, then this is all less than 1. But we know sin squared x plus cos squared x is 1. So the left hand side is 1 plus 2 sin x cos x, and that has to be less than 1. So we could then take away 1 from each side. This results in 2 sin x cos x being less than 0. So let's consider this now. We know x is between 0 and pi over 2 inclusive. In this region, sin x is always positive and cosine of x is always positive. So we're going to have 2 times something that is positive times something that is positive, and that has to be less than or equal to 0, which can't happen, so this cannot possibly be true. 2 sin x cos x being less than 0 is false, can't happen. So it follows that sin x plus cos x is greater or equal to 1 when x lies between 0 and pi over 2. In our solution, we had the situation that 2 sin x cos x was less than 0 when x was between 0 and pi over 2, and we could have spotted that sin 2x is less than 0. So we'll just have a quick look at thinking about sin 2x being less than 0. The graph of sin x, sine of 0 is 0, so it passes through the origin. When it's pi over 2, sine is 1. When it's pi, it's back to 0. So we should know what the graph of sin x looks like. So if we look at the graph of y equals sin 2x, this is the graph of y equals sin x, and it has been squashed in. The sine of 0 is 0 when it's sine of 2x, but when it's pi over 4, 2x is pi over 2, and we get the maximum value of sine 1, but we can see the graph there. But we were interested in what was happening for x being between 0 and pi over 2, and sine 2x was always positive, so this was another way we could have looked at that.
A couple of additions now. The first one is that we have that sin x plus cos x is less than 1, and that then implies that sin x plus cos x squared is less than 1. Now, really, we perhaps should mention at that point in the proof that this is because x is in the interval 0 to pi by 2, and therefore sin x and cos x are both greater than 0, which we use later on in the proof, but it's important here as well because we can't just square inequalities. without being careful. For example, we have that minus 2 is less than 1, but minus 2 squared is not less than 1. So make sure you're very careful about that. And if in a question it mentions that x is between 0 and pi by 2 or something similar, then that's a clue that probably is important, or you at least need to think about why they've stipulated that. I should also close that bracket, because you must always close brackets, and also I noticed that actually this should have been greater than or equal to. Doesn't change the argument, but the eagle-eyed amongst you will have noticed that little slip of mine, and so now that's corrected. Now the second extra that I want to have a look at is the proof of the irrationality of root 2, and that extends to the irrationality of other surds as well, and you will have learnt the classic proof of that as part of Unit 3, and I want to show you an alternative way of completing that proof. So we start off with root 2 is p over q if root 2 is rational, and this gives us that 2 is p squared over q squared, and therefore that p squared equals 2q squared. We also state that p and q is in its smallest terms, and what we can do there is use this notation, which means the lowest common multiple. So the lowest common multiple of p and q is 1, meaning that they are co-prime, meaning that they cannot be cancelled. Okay, now from here you will remember that we can continue this by saying that since p squared is equal to 2q squared, then this implies that p is an even number, so it's in the set of even integers, and therefore p equals 2 times some other number, and then it carries on from there. But there's a nice alternative to that, which is to look at it geometrically. So what we can say is that if we have a square like this, then the area of that square must be equal to 2 squares of side q. So if we give some shading to this, we've got this one like this, and we can shade these ones. Now, what we can now do is, if we take our p square, we can draw our q squares inside it like that. So we have the whole side of that is p, whereas the smaller squares are q. So that's our green ones. I'll do the shading the other way to show that this square in the middle, so this one, which I'm going to make completely green, is the overlap. Now this is not very well drawn to scale, but because we know that the two green squares, the q squares, should fill the p square, then that means that this little square here that was in the middle must be equal to these red squares added together. So okay, now since p and q are co-prime, they are the smallest p's and q's that have this property. But if we look at the lengths of the sides of these little green and red squares, then we can see that the red ones have a side of p minus q, and the green one has a length of side which is p take away 2 lots of p minus q. Now what that means is, because an integer take away an integer is also an integer, so if p and q are integers, then that tells us that p minus q is also an integer. That tells us that the length of the sides of the green and red squares are integers, and there's our contradiction. So if we give these a letter, so we'll call this one big P and these two Q, then we have found that we have a contradiction, which we can do like that, because big P is less than little p, and big Q is less than little q, and therefore our assumption, which was at the beginning, which is that we can write root 2 as a fraction, or that it is rational, is false. So we've shown the contradiction geometrically instead of algebraically.